Thank you all for finding your way to this breakout room. I think it's the furthest from the rest of the action, so I appreciate your making the trek. How many of you were just in the keynote? I'd like to see a show of hands of how many folks saw what we announced today. Great. So you've seen a great introduction from Jay and the value of streaming. And of course, Constantine showed you what our new Flink service looks like. What I want to do in this talk is give you an introduction to Flink and help you understand in more depth what it is, how it works, and what you can do with it. Now, it's been my privilege over the past several years, since 2016, to teach lots of groups about Apache Flink. And I find that I get two different polarized reactions to Flink. Some people come up to me and tell me, oh, Flink is so complicated. I find it confusing. Please help me understand whatever aspect they're confused about. While other folks come up to me and tell me, Flink is so amazingly straightforward, I can't believe how easy it is to use. And I think, so I've puzzled for a while over where this difference comes from. And I think it has to do with the background that you have, that you bring to Flink, and whether or not the concepts in Flink are foreign, like you're trying to learn Japanese or something very different than what you're used to, or whether it's just already like you're already used to understanding the challenges that Flink faces, the problems it solves, and the kinds of solutions that are going to be appropriate. So what I want to do in this talk is help bridge that gap, help you understand where Flink is coming from and why it's designed the way it is. But before we dig into that, I want to give you a quick reminder of the kinds of use cases we're talking about and the value that Flink brings. So we live in a world now where we all have come to expect the companies that we work with to react to the data that affects our lives quickly. So for example, a few years ago, someone rented a car in Prague. I was not in Prague. I did not rent this car. But they used my credit card somehow. And my bank figured this out about an hour later and let me know and helped me work through the process of declining the charge and getting this fixed. It took about a month. It would have been so much better if their model had figured out that there was something wrong here and if they had prevented this from happening in the first place. And that's the kind of expectation I think we're all growing to have in this world. Services that can do that sort of instant reaction to data, they rely on stream processing. They can handle data coming from many different kinds of systems, process it in real time, and produce results right away. And Flink is well suited for this kind of application. Lots of words on this slide. I've tried to outline a dozen different kinds of use cases that folks build with Flink. Let's just talk about the categories here. So on the left, you have ETL pipelines, streaming data pipelines. These are applications that are moving data from point A to point B and doing so continuously. Lots of companies are doing this sort of thing. In the middle, you see real-time analytics. This is, in some ways, a special case of the first kind of application. But here, really, the use cases are a bit different. It's all about, analytics, right? So sometimes this is building features for machine learning models. Sometimes this is about driving dashboards. In many cases, it's about really mission-critical things, like doing usage metering and billing. I think it's a testament to how reliable and robust Flink is that companies are building pipelines with Flink. And in the last case, in the right-hand box, you see event-driven applications. So these really feel rather different. This is about reacting to events as they occur and figuring out what to do with them. So this often involves enriching an event with additional data sources, like maybe it's an event about a credit card swipe, and you need to figure out what you know about where did the previous credit card swipe for this credit card occur? Who is the merchant? Do we trust this merchant? All that kind of stuff. Now, why are developers choosing Flink to build these applications? A multitude of reasons. The first of which is, Flink just works. But more critically, Flink has the runtime architecture needed to achieve really high scale and really high performance. It scales all the way from simple applications ingesting thousands of events per day up to really huge applications ingesting billions of events per second. And it could do all that while giving you correct results all the time. So it's fault tolerant and provides high availability. Furthermore, you can work in the framework of your, well, the language environment of your choice. So Java, Python, SQL, these are all options to you. And whether you need to do batch processing or stream processing, you can write your code once and run it with both execution models. So for example, you might want to run a streaming pipeline on your live data, but backfill historic data, running the same job, but just running it in batch mode to recompute all that historic stuff. For the rest of this talk, I'm going to describe the 4 cornerstones on which Flink is built. I promised you an introduction to Flink in 4 acts. I'm telegraphing up front what the 4 acts are going to be about. We're going to start with streaming. I told you that Flink provides a unified model where you can run your pipeline in batch or streaming. Flink treats batch processing as a special case of streaming. You see on this diagram an unbounded stream. That just means that you start ingesting data and you just never stop. You just run that application potentially forever. If you know up front that you're only going to ingest some portion of the data, maybe you're just going to process data for the past hour, or you're going to start now and run for a day and then stop, that's a bounded stream. Now, I'm going to start to introduce some terminology so that we can talk a little bit more about the developer experience. So, Flink, you see in this middle of this diagram, doing stream processing. Flink is not a storage engine. It's designed to work with systems like Kafka that store your streaming data. So Flink wants to ingest data from data sources, which might be CDC streams from databases. It might be REST calls from applications. It might be files. It might be Kafka. Process the data, and then send it to one of many different sinks that Flink supports, including Kafka, databases, and file systems. For this talk, I want to focus on this part of the diagram in the middle there. Let's dive into what you're doing as you describe the business logic of your streaming application. So we're going to zoom in on this bit in the middle and talk about what we, in the Flink world, call the job graph. If you're more familiar with Kafka streams, this is the topology. This is a graph in the mathematical sense of a graph, where we have nodes and edges. We call the nodes operators, and the edges we call connections. Now, these operators might be doing different things, and they might be connected in different ways. So I'm going to slowly build up a data processing pipeline here. And at the beginning of this pipeline, we have a data source. I'm imagining it's a source, something like Kafka, that has some data that's already been pre-partitioned. So we're connecting to multiple partitions of some, it's different files, or it's different partitions from the Kafka topic. Different kinds of sources partition in different ways. But for scalability, all of the different Flink sources support some notion of partitioning the data. And we're going to be ingesting in parallel from these different sources. So this is critical to scalability. You need to be able to operate independent parallel pipelines of your job. So that's what's happening here. And I'm imagining that whatever upstream process produced this data in the first place had already organized this data and had pre-partitioned it by shape. So you're seeing here some colored shapes. You see the circles on the bottom and the squares across the top. So that's how the data is coming in from, let's suppose it's the Kafka source in this example. And then in this example, we're forwarding the data, just forwarding it downstream to something that's going to do filtering. And in my simple made-up application, I just want to filter out all of the orange events. I'm only interested in the blue ones and the yellow ones. And what I'm going to do then is group these events by color and count them by color. A very artificial example, I admit, but it's similar to the kinds of things people do in real applications. So here we're repartitioning our data streams. And this is expensive in Flink. The forwarding operation that we did, the connection from the source to the filter, that was very efficient. And the data was just exchanged in memory between those different operator instances. But here, where we're regrouping around a different key, We're having to do a network shuffle. This involves serializing all of these events, sending them across the network, deserializing them. It's absolutely essential that we do this for this application because we need to get all of the yellow events to go to the same place so we can count them together in one place. Similarly for the blue events. So we couldn't avoid this, but we're going to pay a bit of a cost for it. And then we have towards the end of this pipeline, we're going to be counting these events. And first we'll have seen one yellow event, and then 2, and then 3, and then 4. Now this is the nature of a streaming application. You don't just wait until you've consumed all the data and say, I saw 47 yellow events and 36 blue ones, because in a streaming application, there's no definite end to wait for. You just have to imagine that the event you just saw might be the last one you're ever going to see, and just keep re-reporting, re-updating the results incrementally. And in terms of the shape of this topology, this graph, you'll see that I changed the parallelism here at the end of the job. I imagined that my sink is operating just as a single instance. I did that just so we could talk about this. It's probably not a best practice because this rebalancing, this changing of the parallelism is also expensive. This is forcing us to do, again, the serialization and network communication that we could have avoided if we'd had 2 independent instances of the sink. Now, this application that I showed you could have been easily expressed as a SQL query. This is what that would look like. I would say insert into results to describe the sink for my job. And the select color and count grouped by color, that's describing this repartitioning and counting that's going on here. The where color is not orange is describing the filtering step. And of course, from events is describing the source of the data. Many straightforward data processing pipelines like this one can be easily and very well expressed as a SQL query. But Flink has other APIs as well. So you see in this diagram a bit of a depiction of the Flink API stack. At the base layer here, you're seeing the Apache Flink runtime. Above that, you see a very low-level stream operator API. And on top of that layer, then you see the public-facing APIs, the data stream API on the left, and the table/SQL API on the right. Why did I call it the table/SQL API? These 2 APIs are very similar in their expressiveness and power. They're both based on the relational model that SQL exposes. The table API is just a way of writing SQL queries with a DSL. So if you're using Java, you get a type-checked DSL that you're writing in instead of writing SQL queries. A bit about the runtime architecture. The code that you write, whether it's a SQL query or you actually use one of the more programmatic APIs like the table API, the code that you write gets turned into the job graph. So you get an in-memory representation of the data flow that's going to happen to execute whatever it is you want to have happen. And that job graph gets submitted to the cluster manager, in this case, the job manager. So this plays the role of orchestrating everything that happens in a Flink cluster. Now this is an important thing to contrast with something like Kafka Streams, which is an application library. Flink runs everything in a Flink cluster. And that cluster is primarily made up of task managers, which is where your application code actually runs. So the job manager arranges for enough task managers to be spun up to meet the needs of your job. And these task managers provide the compute resources to make things happen. So they provide the memory and CPU and network connections and so on. And all of the data flow happens in between these task managers. And the job manager is just sitting kind of alongside that, making sure that everything is still running, restarting task managers as needed, and so on. Okay, that was a quick introduction to the kind of the streaming world as Flink sees it. Now let's talk about the role of stateful stream processing. So looking at the application we were just talking about, if you think about the various stages in this pipeline, first we had this, the first significant stage was the filter. Filtering is a nice example of an operation that doesn't need to keep any state. You don't need to remember anything about previous events to figure out if the current event you're processing is talking about an orange event or not. You can just look in the event and decide what to do with it. So that's completely stateless. But counting, on the other hand, is something that obviously requires that we store something. We have to store a counter, in this case, a counter for every color. So if you were thinking about how to build this, you might think in terms of having a hash table where you have the keys are the colors and the values are the count so far for that color. And that's exactly the kind of state that Flink manages. You can think of the state in this counting operator as a sharded key value store, where each instance has the entries for some of the colors. Now, where does that state actually live? In Flink, the state is always local. It's either in memory on the heap of the Java virtual machine, or Flink can also use RocksDB, which is a local embedded key value store that keeps an in-memory cache, but the ground truth of the state is living on disk, but the local disk. So this scales extremely well because there's no cross-node communication. However, the local memory and the local disk are vulnerable. This isn't a robust place to keep state that will survive failures of these nodes. So Flink relies on a notion of periodically taking remote backups of all the state. And I'll talk about how that works in just a few minutes. But I want to contrast this with the way that I think we all learned to build scalable applications, scalable transactional applications. The way you do that, of course, is you have stateless application servers, and you talk across a network, and you have a database that's maintaining the ground truth of all your data. That's a great way to build a certain category of applications, but it's not a good way to build streaming systems. The latency involved is too great, and scaling up these kinds of databases to handle the sort of load you'd put on them is also an unattractive prospect when you can do something much simpler. Okay, we've talked about two pillars of our Flink engine. Two more to go. Let's talk about time. Those of you who've done streaming before are probably familiar with this distinction. Flink makes a strong distinction between the time when events actually happened, and we call that event time, and here the basis for timing information are timestamps stored in the events themselves, probably recorded there by whatever device created the event in the first place. As opposed to what in Flink we call processing time and what in Kafka streams is called wall clock time, here the basis for timing information is the time as recorded by the system clock when the event is being processed. Now, event time is generally preferred because it gives you this nice logical notion of time that's completely decoupled from how the events are being processed. You can expect deterministic results regardless of the rate at which you are processing the data. Doesn't matter if the data is live or data from last year. You expect consistent results if what you're looking at are the timestamps in the event. So think about an application like counting page views per hour. There's a truth to that you can just expect event time to reveal. If you're counting page views processed per hour, that's going to vary all over the place, just depending on the speed at which you're able to process them. But there's a real challenge to working with event time-based event streams, and that is that events can, and in general will, arrive out of order. A good example of why that will happen, think of an Amazon delivery truck that's driving around doing deliveries, and it's producing a stream of data that's going to the cloud somewhere about these packages being delivered. There's no guarantee that just because one event occurred before another, that it will actually find its way to being processed before the other one. Different events are going to take different paths through the infrastructure. The truck is going to be maybe disconnected from the cellular network for a while, and then it comes back online, and now it's talking to a different part of the cell network, and the data takes a different path to the data center, and so on and so forth. So you really have to expect in general that your data won't necessarily be processed in order. Now, why does that make things more challenging for systems like Flink? Let's just talk through a little example here. So here you see at the right side of the diagram the next event that's going to be processed. This event has a timestamp and some payload. What we're trying to do in this made-up application is count events per hour by key. A simple enough use case. And we've been counting since 1 o'clock, and we're sort of approaching 2 o'clock. And we need to notice when we get to 2 o'clock so that we can finish up that hour and report the results for it. So here's the events that are going to follow. And because they're out of order, it's not exactly obvious at what point we say the hour from 1 to 2 o'clock is done. Yeah, there's some events here that clearly fall into the next hour, but are we really done seeing events that are before 2 o'clock? To figure that out really requires us making some assumption about how out of order this stream might be. There's really no other way to do this. We can't peek ahead into the future of the stream because that's not available to us yet. We just have to accept the data as it comes and make a decision. And the way that Flink handles this is with something called watermarking. And when folks come up to me when they're learning Flink and they're confused about something, watermarking is probably what confuses them like 50% of the time. But all a watermark is a statement about the completeness of the stream at that point in the stream. So in this case, I'm showing you a watermark that says 145, and that's a statement that at that point in the stream, the application is confident that it's seen all the data up to 145. Now, where did that timestamp come from? That's computed by taking the largest timestamp it's seen so far, which is the one just before it there at 150, and subtracting that estimate of the out-of-orderness. So here, I'm assuming that this stream is at most 5 minutes out of date, out of order. And so I've taken 150, I've subtracted 5 minutes, and generated a watermark that says 145. This is just a heuristic. This might be wrong, but it's our best attempt to tell you how to process this stream. And so what should this window that's waiting for 2 o'clock do? It should wait until it sees a watermark that has the timestamp of 2 o'clock in it, and then it can go ahead and safely assume it's seen all the data for that hour. Now this lets you manage a trade-off between latency and completeness. You could watermark aggressively and be wrong more often about whether the stream is complete, and that's fine for some applications. Or you can watermark more conservatively and try to make it as likely as possible that you won't have any late events. But this is just physics. There's really no magic here. There's no better thing we can really do. So if you were confused by all that and are still wondering, what are watermarks for? They're just there to make things happen when the time is right. Often that's to close a window, but it might be to produce the result from a join. There's lots of things in Flink that are waiting for watermarks to tell them that they've seen all the data they need to see, and now they can produce a result. OK, one more important topic to talk about, and then soon we can have some questions. The way that Flink handles fault tolerance is with something that we call snapshotting. We're taking snapshots of the state that Flink is managing. Now let's be clear. A Flink pipeline might be processing a petabyte of data per day, but it's not going to have a petabyte of data that it's storing itself. That petabyte lives in file systems in Flink, in Kafka and other storage systems. Flink might be maintaining gigabytes of data or maybe terabytes of data based on what it's seen in those streams so that it can correctly process the data that's coming in. And that data we need to manage carefully. We need to make sure it can robustly survive failures of the task managers. So We take these snapshots, and they come in two flavors. A checkpoint is one of these snapshots whose purpose is to handle failure recovery. So Flink manages these checkpoints automatically. You don't have to think about them much. You just have to turn this on and configure it, and off you go. A save point is using the same internal mechanism, more or less, to snapshot all the state, but it's a bit of a different kind of a snapshot. The purpose of a save point, it needs to be something that gives you maximum operational flexibility for working with the snapshotted data, because you might need to, you might be doing an upgrade of your job, or you might be doing an upgrade of Flink, and you need to make sure that the data will be able to be successfully re-ingested by Flink after you change the code and change the framework. A checkpoint doesn't have to be as flexible in its operational capabilities. A checkpoint needs to be something that can be recovered as fast as possible, because your goal is to get back up and running as fast as possible, so you want your checkpoint to be in a format that Flink can ingest and start from as fast as it could. But conceptually, what's happening in a snapshot? Well, here's that same job graph that we've looked at a couple of times now. Let's talk about the different stages, the different operators in this pipeline, and the state that they have, and how that's going to get recorded into either a checkpoint or a save point. So we have these 4 different operators. We have the source, the filter, this aggregating step, and the sink. The event source does have some state. If this is the Kafka source, it knows the offsets of each of the partitions that's consuming from. And so at the time that we're taking a snapshot, we will record the current offsets, meaning this Flink job has consumed all of the data up to those offsets that we record here, and nothing passed. The filter doesn't have any state. The counting step is keeping counters. Now, to have this be a globally consistent snapshot, we need to take care that these are the counters that correspond to having read the data that we recorded as the offsets for the sources. So we've consumed that much of the input streams, and we've counted this far. Those two go together, and the sink is going to record the transaction ID, the Kafka transaction ID, for the transaction that commits those counters. So we get here a completely consistent view of the data at some point in time. What's impressive about the way this is handled is that taking this snapshot is done without interrupting the continued ongoing processing of your streams. So Flink just continues to march on, processing your data while this is happening asynchronously in the background. So getting that to work, it's not simple. There is some, I want to argue that the Flink APIs are not that hard to learn, but operationally and in the runtime, there's a lot of wizardry. Because these snapshots are self-consistent, there's a few things to understand about this. This means that you can rely on having what are effectively exactly once guarantees. Flink will, in the event of a failure, rewind back to the most recent checkpoint and start consuming again from there. And so obviously some data will be re-ingested and reprocessed, but it's as though that hadn't happened, because you rolled back everyone together in a coordinated way. But that also meant that you had to restart every player in this system. If you've got a parallelism of 1,000, most likely the whole cluster is going to have to roll back to the most recent checkpoint and start from there. Okay, going to wrap this up. We've talked about 4 things, and I want to kind of give you kind of how I think about them. Stream processing may be unfamiliar to you. It's certainly unfamiliar to many people in our industry. Ultimately, I think once you get some experience with it, it actually feels very straightforward and very natural. You just have to dive in and start using it a bit. And for me, it took about a month of working with Flink before I woke up one day and it all made sense. It was a bit like the first time I drove in England. Boy, the first day I was panicked about doing everything backwards. But somehow my brain absorbed that all overnight, and I woke up the next day and driving on the wrong side of the road was just as natural as being on the right side of the road. And it was that way for me with streaming too. Suddenly I just understood how the runtime works, and the rest was straightforward. Flink's model for handling state, I find it delightfully simple. It's just a key value store, just a distributed key value store. You can only access the local state, and you don't have to think about concurrent access or threading because the way that the APIs are organized, the code you write for a single operator runs in a single thread, so there's nothing hard here. The timing stuff, again, is foreign, it's new, but it encapsulates something that is potentially complex in one place. And all you really have to worry about is to think about how out of order can each of my sources be, and can any of them become idle? And you just have to parameterize your watermark strategy with those two factors, and Bob's your uncle. Or you use, as Konstantin described, we're going to take all this pain away and give you auto watermarking that just works. And then finally, I talked about this snapshotting mechanism. Operationally, it's again has lots of knobs you can turn and configure. But as a developer, you just can rely on the fact that everything's going to work and you're going to get the right answers. And it's nice to understand how that happens underneath the hood, but it's not really your problem. If you want to learn more about Flink, I invite you to look at my course on Confluent Developer. This is an introduction, sort of expands on the things I've talked about here, and that gives you some hands-on exercises you can do to make it all feel more real. And my colleague Wade also has a great course. This is about learning the Java APIs for building Flink applications. And for all that content and more, please come to Confluent Developer. So thank you for your attention, and now I'm happy to take questions.